Hi guys, I just wanted to go over these Chapter 5 problems that I assigned on Monday when I was not in school. It was the classwork assignment that you had to do and then finish for homework. So if you want to pause the video and take out these problems from last Monday. So I'm going to go through most of them and you can check your answer, you can check your work. Number 1, the function was x times the square root of 2 minus x. And the question wanted you to find global extreme values of the function and where they occur. And then for number 1, they gave you an endpoint. Endpoints are awesome. So first thing we're going to do is address the domain of this. And the domain, actually, I'm sorry, we don't have to do the domain of this because the domain was given for this problem. First thing we're going to do is find the derivative using the power rule. X is going to stay. The derivative of this is going to be -1. So I should have made that be a negative. I'm doing the chain rule, and then this is what it ends up being. So the derivative of x is 1. This is going to stay. X is going to tag along. The derivative of this quantity, if I do the chain rule, the derivative of the inside is -1 times the outside derivative is 1 over 2 times the square root, and I throw back the inside function. We should go find the critical points. You should take a common denominator. And then the common denominator ends up where I'm going to multiply this by this denominator. So it's just 2 times 2 minus x. And then this is just going to stay. That's the common denominator. I'm going to put the numerator equal to 0. So it's 4 minus 2x minus x equals 0. The derivative doesn't exist if my x is bigger than 2, but that's not part of the domain. I'm stuck between -2 and 2. Right, if I plugged in x as -5, if I plugged in x as 5, it would produce a negative denominator. The other point where the derivative doesn't exist is if x is 2 and -2. But 2 and -2 are part of the domain. So I'm hoping you're realizing that situation, that the derivative is not going to exist at those endpoints. Alright, let me finish this part. It's 4 minus -3x equals 0, 4 equals 3x, and x equals 4/3. This is a critical point. Again, I know the derivative does not exist at plus or minus 2. It does not exist. But they're the endpoints, so I can't call them critical points. Anyway, the question wasn't really looking for critical points. The question was looking for absolute max, absolute min. I'm going to plug in -2 into my original function. I'm going to plug in this critical point. I'm going to plug in the other endpoint, which is 2. The largest value ends up being the absolute max, and the largest value comes from when x is 4/3. It's 4 root 6 over 9. This is the absolute max. The smallest value comes from when I plug in -2. Because when I plug in -2, I get -4. Remember, I'm plugging them into the original function. And this produces the absolute min. They wanted both the y value and the x value. Okay, I'm going to be honest. 3 is not a good question to do without a calculator. So for 3, the original function was kind of complicated. Like, this is the original function for 3. Finding the derivative once isn't all that bad, product rule and the chain rule, but then finding the second derivative gets really complicated because the first derivative is really complicated. So here's what I would like you to do for 3. I would like you to go through all the parts for 3. They asked a bunch of things. Where is the function increasing, decreasing, concave up, concave down, local extreme values and inflection points. Go do number 3 using your calculator. Go graph the derivative. Like, don't just go graph y. Use calculus, but get the help of your calculator. So that's how you should do number 3. I'm going to go on to number 8. Number 8 was also asking for all those things. Here is what 8 looks like. It's x over x cubed minus 1. That was number 8. No domain was specified, but I know that I can't have x to be 1. I know that. I'll make the denominator be 0. This is a rational function. I know that this graph is going to have a vertical asymptote at x equals a. So vertical asymptote. Again, this question was not looking for absolute max, absolute min. This question, why do I think I changed the question and said, go find absolute min, absolute max? I think I did add that in. But the original question in the textbook was asking for where is this increasing, decreasing, where is it concave up, concave down, local extreme values, and inflection points. Okay, we addressed the domain. Let's do the quotient rule. Let's go find the derivative. X times, this is 3x squared. Okay, if I take the numerator and I simplify, I end up getting 6x squared times x cubed plus 2, and the denominator stays put. Okay, I'm going to put the derivative, the numerator equal to 0. And when I put the numerator equal to 0, I apologize. This is not what we get. That's the second derivative. Sorry about that. So if I go simplify this, let's try this again. I will get 2x cubed plus 1. And I'm hoping you also got that over x cubed minus 1. This is the first derivative. And when I put this equal to 0, I get negative 1, divide, and I get the cube root. This will go on my number line. I get the cube root of that negative 1/2. So here's the part that's awkward. The part where this graph was discontinuous because of vertical asymptote, that also goes on the number line. What if my derivative changes signs at that point where the graph jumps because it's discontinuous? Okay, I'm doing the first derivative test. If I plug in, this is where I'm going so I don't forget it. If I plug in 3, the denominator is positive. The numerator, if I plug in 3, am I doing this right? If I plug in something bigger than 1, did I make a mistake somewhere? 3, oh, this is a minus. Is that a minus 1? Sorry, bear with me. This is going to be x cubed minus 1. This is going to be minus 3x cubed. And then when I combine like terms, I get negative 2x cubed minus 1. So something's not right. Did I copy the problem wrong? I didn't. Okay, let me make sure I did the quotient rule correctly. First of all, that whole thing is squared. The derivative of the top is 1. This is the bottom minus, this is the top x, and the derivative of this is 3x squared. Okay, this is x cubed minus 1 minus 3x cubed. This ends up being negative 2x cubed minus 1. Okay, so that's not right. Negative 2x cubed minus 1. And when I put that, okay, you know what I meant to do? I meant to take out the negative, but too late now. Okay, that's my numerator, and if I put this equal to 0, negative 2x cubed minus 1 equal to 0, as I add 1, something bigger than 1, this is positive. If I plug in like 5, the numerator is negative. So this whole thing is negative. Okay, this is going to produce a negative answer, so let's plug in 0 in between. If I plug in 0, that's negative. And if I plug in 0 here, that's also negative. But I'm getting a negative answer here. So let's see, if I plug in 0, because 0 is between these two. Yeah, the book shows negative. Let me just confirm that really quickly, because I think the book shows a negative for that one. Sorry if there's like dead silence because there's no pause button on the video camera, so you're just gonna have to bear with me. Okay. Why does the book have a different derivative than I have? Okay, maybe they made a mistake. I don't know what's going on right now. Alright, I'm going to make another video for 8 because I don't want to waste your time, and my answer is just coming out different than from the book. So, this is my derivative. I know this is still squared. I know that's right. If I plug in something bigger than 1, oh, I figured it out. Because the square was missing. Alright, okay. So, if I plug in 0, the bottom is positive. And if I plug in 0, the top is negative. So this is negative. It's that darn square that I forgot to bring. Okay, if I plug in something that's like negative 5, if I plug in like negative 5, the bottom is going to be always positive because it's squared. But if I plug in something like negative 5, this negative and the negative cubed will turn into a positive minus 1. It will be positive. Okay, so this will give you that there is a local, you know where your f is increasing, you know where your f is decreasing. Please write a sentence and don't rely on the number line. They're looking for local min, local max. You know there's a local max where the derivative changes signs from positive and negative. There's a local max there. Then there's a local min. Well, actually, there's no local min here because the derivative never changes signs from negative to positive. Okay, we're not done. Now we have to find the derivative of this. Negative 2x cubed minus 1 divided by that. We need to do the second derivative. So, quotient rule one more time is what we're doing. And I've already found it. That I actually wrote it right here. So I already found it, took the derivative and did the quotient rule one more time. So here is the second derivative, y double prime equals 6x squared times the quantity x cubed plus 2 all over x cubed minus 1. Things simplified, so I'm hoping you also simplified it, and that's what you got. So the second derivative, we're going to draw my sign chart because we want to find inflection points. First thing that's going to go on our sign chart is where this, I'm going to put the numerator equal to 0. This equals 0 when x equals 0. This equals 0 when x equals negative cube root of, actually, let's take the negative out. It's the cube root of negative 2. And now we also have to throw back that 1. That 1 is where my vertical asymptote happened. And again, my inflection point can change there, so I'm going to put the 1 there. Okay. I'm going to do my sign chart, and I'm going to plug in something bigger than 1. If I plug in like 5, this is always positive. This is positive. If I plug in 5, it's positive. And then here, if I plug in 5 and cube it, it's still positive. If I plug in 1/2, so if I plug in 1/2, this is going to be negative. That's positive, but the whole thing ends up being negative. You know what? I don't know what decimal is in between there, so feel free to use a calculator. Wait, I know negative 1 is in between there, never mind. Because this is the cube root of negative 2, so negative 1 is in between there. If I plug in negative 1, that's positive. If I plug in negative 1, that's positive. If I plug in negative 1, this is negative. And the whole thing ends up being negative. If I plug in like negative 5, the whole thing ends up being positive. Okay, inflection points, you've got 2 of them. One inflection point and another one. Please write a sentence. It happens where the second derivative changes signs. They're also looking for concave up, concave down. Please write a sentence where the second derivative is positive. Y is concave up. So y is concave up from 1 to infinity. Write a sentence where the second derivative is negative. Y is concave down. Okay, guys, bear with me. I'm going to move on to number 27. 27 wasn't that bad. They just wanted you to find the linearization. The function was tangent of x. Linearization is just the equation of the tangent line. And then the point of tangency they called A was negative pi over 4. Again, point so form, you want the derivative at negative pi over 4. This is that. And then this would be the y value at negative pi over 4. Find the derivative of tangent of x, and which is cosecant. Sorry, it's 1 over cosine squared x. Plug in negative pi over 2, that's the slope of the tangent. Plug in negative pi over 4 to tangent, and that's the y value. So 27 wasn't that bad. 33 wasn't that bad. Here's number 33. Please write a sentence for number 33. It was asking for where is f increasing. F increases where the derivative is positive. You need a closed bracket. Where is f decreasing? Where the derivative is negative. Estimate any local extreme values. Please write a sentence. It's where the derivative changes signs from positive to negative. So there is an extreme value, a local max at what am I looking at? At x equals, this is the derivative. So the derivative changes signs from negative to positive at this point right here. And then the derivative changes signs from positive to negative at this point right here. Do not forget the endpoints. Look how the endpoints are both like filled in, and you also want to consider if at -3 there's a local max or not. So think about this. The derivative is positive from -3 to -2. If the derivative is positive and your graph of f is increasing, that means this left endpoint, which is -3, ends up being a local minimum. Okay, let's look at this endpoint too. The derivative is positive at this endpoint. That means my graph of f is increasing from 1 to 2. So if my graph of f is increasing, this top point right here at x equals 2 ends up being the local maximum. So it's a local maximum occurring at x equals 2. There's a local maximum occurring where the derivative changes signs from positive to negative. So local max at -2. There's a local min at -3. And there's a local min at x equals 1. Okay, that was 33. Last one. We're looking at 37, mean value theorem. Mean value theorem. So they wanted you to say if this, I meant to write 37, and the function is x times ln of x. And they wanted to make sure in part A that this f satisfies the hypothesis of the mean value theorem on this interval on 0.5, 3. You know you cannot take the natural log of 0, but 0 is not in here. You know you can't take the natural log of a negative is not here in here. So this function is continuous on this interval. Let's see if it's differentiable. We have to find the derivative. Let's do the power rule. The derivative of x is 1, natural log of x stays. The derivative of natural log of x is 1 over x, and then 1 over x times this x just turns into a 1. So here's my derivative. This derivative does exist on this interval. Again, we don't want 0 for my natural log, and we don't want negatives, and none of that's happening on this derivative. That was A. B wants you to go find that special value where the derivative is equal to the average rate of change. So here's the derivative. And now let's go find the average rate of change. Average rate of change is going to be f of 3 minus f of 0.5 all over 3 minus 0.5. I think the numbers get really ugly because it's x, like natural log. So f of 3, this is me finding average rate of change. I'm going to get that value, which is going to be ugly, and put it equal to the derivative. When I plug in 3, it's 3 ln of 3. Plug in 0.5, it's 0.5 ln of 0.5. And then when I subtract, I get 2.5. It's ugly, but it represents some number. If you want to use the calculator, there was no gray box. So if you want to use a calculator and turn it into a number, that's okay. We're going to put this equal to the derivative, and we're going to solve. We're going to solve for what x is. So whatever this ugly value comes out, you're going to subtract 1. So I don't know what the ugly value is, but I'll just call it blah. We're going to subtract 1. That's what equals natural log of x. And to solve for x, because you want the ln to go away, you're going to raise both sides. to the power of, with the power, these are going to be the exponents and the base is going to be e. It's called you exponentiate both sides. So you're going to take e to the natural log of x, which just turns into an x, which is what we want. This right side is going to turn into an x, and then e raised to this whole thing minus 1 is what x equals, and you should get 1.579. So your exponent is going to be 3 ln of 3 minus 0.5 ln of 0.5 over 2.5 minus 1. That's your exponent, your base is e, and make sure you get 1.579. The equation of the tangent of the secant line in C, that's pretty simple. The equation of the secant line in C, well, this ugly number represents the slope of the secant line, whatever that decimal is, and then so it's y equals whatever this decimal is will go as the slope. Let's choose an x value. We can choose the x value to be 3, and then the y value at 3 is 3 ln of 3. But this decimal is the slope of the secant. D wants the slope of the tangent. So this is the derivative. The tangent line is drawn at the point that you obtained in B, because that's what you're looking for. B, you're looking for where is the tangent line parallel to the secant line? Where is your instantaneous? Where or when is your instantaneous speed equal to the average speed? So the answer that you obtained for B, that 1.579, that is the point of tangency. Wait, I'm so sorry. I'm just making it so much more complicated. I apologize. The secant line and the tangent line are going to be parallel. So if the slope of the secant line is this, like duh, we put them equal to each other. If the slope of the secant line is whatever this ugly number is, that's the same ugly number that was B here. The only difference is your point of tangency is your answer for B, from B, which was 1.579, plus you just need the y value at 1.45. Oh, am I doing this right? Is it? Yeah, 1.579. That's the y value. Plug that into your calculator, and hopefully the answers in the back are the same as what you got. Okay, thanks for watching.